Awesome. So in that first video, you should have learned a whole lot about the reaction pathways. Kind of talking about a few key points. So I'll go ahead and label them in here. So again, we're going to pull all the way across that starting point and that ending point. So the two key points are the E of A, or the activation energy. So that's going to be from the start up to the crest. So there's our E of A, our activation energy. And then again, our delta E, or our change in energy, is going to be from the start to the finish. There is our delta E, our change in energy. So keep in mind that since we started up here and we lost energy, that means we've released energy, and this would be considered an exothermic reaction. Awesome. So in here, again, the biggest point, the most important point to kind of pull from this graph is this kind of point here, the activation energy. So with our rate of reaction, there's a lot of things that we can do to kind of decrease this activation energy to make it a little bit easier. So to think about it another way, if you're climbing a mountain, this would be kind of like Mount Everest. So instead of Mount Everest, we can think about just climbing like a small hill. If you're not necessarily a practiced climber, you might prefer the hill over Mount Everest. And so our reactions kind of prefer the same. We always like to think of our reactions as being kind of lazy. They want to exhibit as little energy as possible. So what we're able to do is, if we were to lower this activation energy, so I went ahead and added a blue dotted line, just like so. This would be the new activation energy, so it's much lower. So there's a lot of ways that we can do this. There's 5 ways that we can do this in this course. So let's go ahead and talk about the first one. So when it comes to this, just lowering the activation energy, this can be done with a catalyst. So this is the first thing to decrease the rate of reaction. So the catalyst just provides kind of an alternate route for the reaction to take place. So instead of climbing all the way to the top of Mount Everest, it climbs just a small hill to have that reaction happen. So with this one, the reaction will happen more quickly. And that is because it lowers the activation energy. So that is how the catalyst is helping. So this is our first way to lower it. The second way to increase our rate of reaction is with surface area. So to do that, by increasing surface area, there's more locations for the chemical reaction to happen. So a way to kind of think about this, if you had a hot cup of tea, right? You got a nice warm cup of tea. I know it's chilly out there right now. And you had a cube of sugar. The only places that that tea could touch to kind of dissolve the sugar is the outermost layer. So all that sugar on the inside of the cube isn't being touched at all. But if you had granulated sugar, just little tiny grains, that tea is able to wrap around every single portion of those granules. So it's going to be able to dissolve much more quickly. So if you're comparing one to the other, on this one you have the surface area of every single little granule, while with this one you only have the surface of the exterior. So an example of this could be if you ground something up. So if you ground it up in like a mortar and pestle and you grind it down from a big substance into little tiny granules, you're increasing the surface area. Another example would be to make an aqueous solution. So if you dissolve it in water, you've increased the surface area. And both of those are going to increase the rate of reaction. This means it's going to be happening reaction quicker. So increase rate of reaction, increase the surface area. Our third one we can talk about is the concentration. So for this one, we kind of have to dive in a little bit more with what's called collision theory. So we're going to go ahead and take a pit stop real fast. So when it comes to collision theory, there's a couple important things. So collision theory is all about the rate of reaction. So in order for a chemical reaction to occur at all, you have to have some key points. The first thing is your compounds have to collide with each other. So for instance, if you had one substance in one bucket and another substance in another bucket, the two are never going to interact. They're separated. So there's no way for them to ever form a new substance. So the first thing is they have to collide. They have to interact. They have to be close to each other. The second part is they have to have the correct orientation. So a way to think about this one is they have to be oriented correctly. So when we go back to Unit 5 and think about our molecular structure, there's specific shapes, and if it's too clustered or too crowded, a reaction might not be able to happen. So think about it in terms of this marker. If I wanted my lid to react with this marker, there's only one way that these two things can react. They can only cap. In fact, we'll even consider another successful reaction. We could say it could also cap on the back. Those are two successful kind of reactions that could happen. So you could either hook onto the back or hook onto the front. Either one is fine. So when it comes to correct orientation, these have to be just like so, either just like this or just like this. If it hits anywhere else, nothing is going to happen. It doesn't matter if it's flipped. So there's a million ways that this could hit, but because it doesn't have the correct orientation, nothing's going to happen. It's not going to be able to have that true bond that you want to see happening. And in the same way, I have to add a certain amount of pressure to kind of make this lid really stick onto this marker. Our last point is that you have to have enough energy. That means you have to have enough activation energy. Or we'll say activation energy met. So for instance, even if this was collide with each other with the correct orientation, if I don't push it hard enough, I don't have the energy to push this lid on, then it's not going to happen. It'll just come back apart and it could come back together, but it still isn't going to form the correct connection which I want. You have to add that energy to really make that snap. So it's the same with our chemicals. With our compounds, they have to collide correctly, they have to hit each other with the correct orientation and enough energy to make that reaction happen. So just like when we were looking on here, you have to hit that activation energy in order for it to bond. Awesome. So let's jump back to it. So if we're looking at concentration, this one is really increasing that first part of collision theory. This is increasing collisions. So a good way to think about this is if you have a couple people in a room, let's say we have 3 people in a room, and let's say they're doing yoga or something. So now they're raising their legs, they're moving their arms, they're doing all these different positions, all this stuff. The likelihood of them bumping into each other is pretty rare. There's plenty of space for them to spread out. They could even have their mats out, and it's not very likely that they're going to hit each other. It's just not likely. They have plenty of space. They're not going to kind of bunch up together. But if we were to increase the concentration of people in this room, or increase the number of yoga participants, so y'all are going to see what's going to happen. Uh-oh, a couple of those people are going sideways. Now, if we have all of these people in one room trying to do yoga, it's going to be very packed. It's going to be like sardines in a can trying to do, the downward dog or whatever. So now the collisions are going to be much more likely. They're going to swing their arm, move their arm, and they're going to just bump into each other because there's not enough space. So by increasing concentration, you've increased the collisions, which is a pivotal part of our collision theory. So increased concentration, increased collisions. Awesome. Let's talk about our next one. Number 4. Temperature. So with temperature, if you're adding heat, that's the same as adding energy. So if you think about a little kid at home, I'm talking about like a little kid just hanging out. If they get an energy drink, like a 5 or 6-year-old, if you give them an energy drink, let's give them a Monster, not 10 minutes later, this kid is going to be running everywhere, back and forth, back and forth, back and forth, moving more and more and more and more and more. So again, you've added this energy, which again is going to increase your opportunities for collision. The other thing with this is that it's also going to be increasing the activation energy, because the more energy you have, the more likely you are to hit that activation energy. So as soon as you're able to hit that peak, you're able to fall down into that bond. So for this one, increased temperature will increase your rate of reaction. Awesome. And then our last one's just a little weird to conceptualize. So number 5 is pressure. So this is our 5th and final kind of factor with our rate of reactions. So let's imagine we have, again, a container. And let's say we have some molecules in there. Let's say we have 10, 3, 4, 5, 6, 7, 8, 9, 10. So that's a pretty good number, right? But if we were to increase the pressure, and so let's do this by decreasing volume. Sorry, don't mind my little flag. We're just going to ignore that. But let's say we just decrease the size of this, but still had 10 molecules. Now it's just much more cramped, and the pressure that these little particles are exerting are going to be much higher. So by increasing the pressure, you're once again increasing the energy. So by increasing the energy, the same will apply. So you've increased the energy, which means you've increased the rate of reaction. So increased pressure equals increased rate of reaction. Awesome. So those are the 5 different factors that you can use to kind of increase your rate of reaction. So again, your first one is have a catalyst. That will give an alternate pathway so that the activation energy is lower. Some other things with our catalyst, just make sure it's not used up. So our catalyst is not part of the true reaction. It's just something that's changing the pathway. The second one, surface area. Increase that surface area and the reaction will happen more quickly. Increase concentration, increase rate of reaction. Increase temperature, increased rate of reaction. And increased pressure is an increased rate of reaction. So make sure to go ahead and go through this next page in that packet. It says rate of reaction, and I will post an answer key for this. The most important part I'm going to want you to focus on is this part up here. So make sure you're really working with this graph and kind of going through those questions, okay?